Okay, in this video we're going to discuss the second type of bond that we're covering this unit, and that is an ionic bond. Alright, this is much different than a covalent bond, where we saw two or more elements sharing electrons to become stable. With ionic bonds, the ability to fill all elements' outer valence shells is impossible. So in order for these elements to be able to bind together, they're going to have to become ions. All right, where one or more will become cations and one or more will become anions. So again, all atoms involved, like I just said, will not be able to fill their outer valence shells by doing any type of covalent bond, either polar or nonpolar. And once they become ions, what do opposite charges do? They attract and combine with one another. All right, so the thing is with this process here for ionic bonds that you will only ever see this happening between metals and nonmetals. So in particular for metals, we're going to be looking at groups 1 through 3. And for nonmetals in particular, we're going to be looking at groups 15 through 17 will become the anions. So again, cations in groups 1 through 3 will bind with anions that are formed that are in groups 15 through 17. And you can kind of see in these two animations down below a little bit what I'm talking about. I got two different versions. I have one for sodium and fluorine combining. If you remember, sodium has the atomic number of 11. So that would be 2 electrons in the first energy level, 8 in the second, and 1 in the third. All right, only has 1 in the third. It's impossible to get 8 with that, so it is going to get rid of that, drop down to the second energy level, which is filled with 8 electrons, and it'll become positively charged. And you can see that on the left directly below for sodium, especially right here. You can see sodium is going to get rid of that electron. The third energy level disappears, and it becomes a positive cation. While if we look at fluorine over here on the right, it's going to gladly accept that electron, fills its valence shell, but now it becomes a negative anion, and then the two of them will attract each other. They never actually touch and overlap energy levels. They just have that attraction between the opposite charges. So any type of ionic bond or compound that you see, we don't make molecules with ionic bonds, right? Molecules are just for covalent bonds. So we're just going to say compounds. It's going to be a salt. All right, it's pretty much just a big crystalline structure of lots of sodiums and either lots of fluorines or chlorines, whatever else is in there, attracting one another. If we look over here on the right hand side, we can see sodium and chlorine creating an ionic bond. Once again, you see sodium getting rid of, that'll be right down here, you saw it moving over, getting rid of its 1 electron. Here it comes. It becomes a positive ion, gets rid of its third energy level. Chlorine, you can see, is accepting that little blue electron, fills its third energy level, and becomes negatively charged. And then again, opposites attract. So again, this is going to be when two elements become ions. You're going to have a metal that becomes a cation, bind with a nonmetal that becomes a anion. So again, most elements in groups 1 through 3, except for hydrogen, as I said, will always donate an electron to an element that you find over in groups 15 through 17. So in the example below, you see calcium. Calcium has 4 energy levels, but it has only 2 electrons right here in its fourth outer valence shell. It only has 2 to give, so it can only ever get 2 in return. That would be a total of 4. That's not 8. It can never reach its octet. So what it's going to do is it's going to get rid of those 2 electrons. So it needs to find either one or more than one element that's willing to accept those 2 electrons. In this instance, we're going to use 2 chlorines because each chlorine only really needs 1 more electron. So over here, you can see now calcium has dropped down to the third energy level, which is stable, but it lost 2 electrons. So we got to make sure we remember it's now a 2+ charge. So I'm going to need 2 negative charges to be able to cancel that out. Well, I get that right here with these 2 chlorines. Each one has accepted an electron to fill its outer valence shell, but now each one is negatively charged. And now we have opposites attract. Your charges always have to cancel out each other when they come together to form an ionic compound. So you have a 2 plus charge, you're going to need a 2 negative charge in some fashion. So, how are we going to draw these virtually? Normally, like you just saw on the last page, we would draw all the energy rings in class if we were actually in the classroom right now, and do exactly what you see going on pretty much right down here in this picture, where you can see the transfer of electrons with the little arrows, and the only thing that's missing is you telling me that calcium is going to be a 2 plus, and then each of these chlorines is going to be a negative. I really want you to show me that. Well, what we're going to do is we're going to use Lewis dot structure like we've been doing for covalent bonds, but we're going to do a hybrid of both of the versions that you see below. All right, so here for A, you can see all the energy rings. In particular, I like to see these arrows here for the transfer of electrons. And down below here, let's say in version B, we see it with just the valence electrons. We see the transfer of electrons with the little red arrows over here. And then on the right-hand side, we see the charges. All right, so what I'm going to ask you to do is this. I want you to pretty much do it exactly like you see down here. But when you see a cation, I don't want you to leave it empty like they're doing down here. I want you to show me that it's now dropped down to the next energy level that is filled, as well as indicate the charge. So what do I mean? So if I erase some of this right now, all right, just so you can kind of focus in, I don't have all this nonsense over here. All right, so remember, calcium, 2 in the first, 8 in the second, 8 in the third, and 2 in the fourth, which is going to get rid of. So its valence electrons are now going to be 8. So I'm going to want you to do your brackets, draw the elemental symbol, indicate the charge, which is going to be a 2 positive, and then I do want you to show me that it is going to be fully stable with an octet now in that second energy level. So again, I have 8 little dots all the way around. If I just draw them a little bit bigger so you can see them clearly. So instead of doing this down here, I want you to show me that it's dropping down to its full octet in the next energy level. Then we have, in this instance, since we're doing calcium chloride right now, we have 2 other chlorine atoms to worry about. So we're going to draw both of those. All right, each one of them is going to accept one of those 2 electrons from calcium. So I want you to indicate that to me simply by drawing arrows like this. They're going to accept an electron, which is going to fill their octet, because they normally only have 7 valence electrons, chlorine. And finally, we better make sure that we put the correct charges outside. And we have 2 plus charge, that's going to attract 2 negative charges. Boom. That's the way I want us to do it. A lot of times in the circle version down here, sometimes chemists do not bother putting the electrons for the lower energy level. They're just making the assumption that they know that. I don't know that you know that. I want you to show me what it now has in its lower energy level by drawing that next energy level's octet. So let's do 2 examples here before we get out. Let's do sodium chloride, basic salt that you have on French fries, pretzels, you name it. So for your knowledge, again, sodium normally has the atomic number of 11 and chlorine the atomic number of 17. So that's 2 in the first, 8 in the second, and 1 electron in the third. Chlorine, 2, 8, 7. It only needs 1 more. So sodium is going to get rid of this because it has no chance of getting another 7 electrons. All right, and remember, it is also a metal, so metals always become the cation. And what I could do now is I can draw the Lewis dot structure for sodium. It lost that one electron, so it's dropped down to the second energy level, which is filled. We already made a notation of that up above. But let's make sure that we indicate the charge. It's now a positive charge. Chlorine, again, normally only has 7 electrons, but it's going to pick up an electron that sodium is getting rid of. So I need you to show me that arrow. Now it's going to fill its octet. You don't have to color in the electron a different color that's coming from sodium. I'm going to realize, and you should realize at this point, that that's what's happening with the arrow. Then make your little negative charge, and you're done. You just drew me the Lewis dot structure for the ionic bonding of sodium chloride. And last but not least, let's do magnesium sulfide. All right, magnesium has 12 total electrons. So that means, again, 2 in the first, 8 in the second, and then 2 in the third. Sulfur has a total of 16 electrons. So what? 2 in the first, 8 in the second, and 6 in the third. It needs 2 more electrons. All right, so what magnesium is going to do, it's going to get rid of those 2 electrons and become a 2+ cation. So Mg. It's dropping down to the second energy level, which does have 8 electrons, so I can fill in that octet. And let's make sure we account for the charge. It lost 2 electrons, so it has to be a 2+ charge. And then finally, over here for sulfur. Sulfur would normally only have 6 outer valence electrons right here, but it's going to pick up 2, and let's draw 2 arrows to indicate 2 electrons are being given off over to sulfur, which is now going to fill its octet. Now its third energy level is filled, but let's make sure we do the correct charge, which is a 2 negative charge. So 2+ will attract a 2 negative, and you have a magnesium sulfide salt. So the key is to remember that you're drawing the Lewis dot structures, showing me that if you drop down, if you're a cation, if you drop down to an energy level, I still want to see that octet like I did here for sodium and magnesium. And then show me the electron transfer with an arrow. So give me 1 arrow for every electron that's being given off and show me where those electrons are going. Down here in our last example, sulfur is collecting both electrons from magnesium, so I just drew both arrows going directly to sulfur. In the previous example, we saw calcium chloride, which was CaCl2, where I had 2 Cls, each accepting just 1 of those electrons, so I drew 1 arrow to each one of them. Hopefully this clarifies things, and use this information to work on your homework this evening. Thank you.